Hello, everyone. Good evening. Welcome to our virtual stream processing meetup. My name is Celia, and I manage the Brooklyn and Data Pipelines team at LinkedIn. My co-host is Christo, and he's a TPM for stream processing and data pipelines, also at LinkedIn. First of all, thanks to each and every one of you for taking the time out of the middle of your week to join us online today, especially during the time of the year where a lot of folks may be winding down to celebrate the holidays. As we enter into the holidays and the end of this unusual year of 2020, we wanted to share with you some of the exciting work that we've been doing in Streams Infra at LinkedIn. So we have two exciting talks for you today, both by our very own LinkedIn engineers. Giving the first talk are Yixing and Bingfeng. Yixing is a dev on the Samza team, and Bingfeng leads one of the performance teams here. Together, they partnered on performance benchmarking for Beam Samza Runner, which allowed them to discover and address several performance bottlenecks. And as a result, they were able to increase the throughput of the Samza Runner in their experiment by more than 10x. So after that, we'll hear from Efe, who is a dev on the Kafka team, specifically leading development on cruise control. So some of you may be familiar with cruise control, which is a system that automates management of Kafka clusters by monitoring the cluster and performing various remediation actions when an issue is detected. Efe will talk about a new feature called Concurrency Adjuster, which enables the execution of these remediation actions as fast and as safely as possible. So before we get started with these great talks, for those of you who are joining us for the very first time, I'd like to answer some of the most frequently asked questions that we get. So are these talks recorded? Yes, they are recorded and we post them onto YouTube. You can search for Stream Processing Meetup LinkedIn on YouTube. And additionally, these videos will be available on our Meetup event site after this Meetup. If you're interested in presenting, there are several options. Please post a message on the Meetup site or LinkedIn message Christo Danchev or myself. Alternatively, you can email me at ckung@linkedin.com. So how can I ask questions to the presenters? So normally when we have these meetups live in person, there's usually a mic stand where at the end of every single presentation, people can just go up to the mic and directly ask the presenters their questions. But in this virtual format, we have the Q&A section on BlueJeans. So please post questions that you might have during the presentation at any time using the Q&A tool on BlueJeans. And time permitting, at the end of each talk, we will take some time to relay the questions to the presenter so that they can answer. And all of the Q&A will be transcribed and posted to our Meetup site after the event. Great, so without further ado, I'll pass the baton to Yixing and Bingfeng.
Thank you, Celia. Let me share my screen. Cool. So hi, welcome everyone. Thank you for joining our presentation. I'm Yixing from the Samza team at LinkedIn, and we also have Bingfeng from the performance team at LinkedIn today. So earlier this year, Bingfeng and I did some work on benchmarking the performance of Beam Samza Runner. Then based on the benchmark results, we were able to find the performance bottlenecks and also worked on the improvements. In today's talk, we are going to share with you the benchmark results and how we improved the performance for Beam Samza Runner. So here's the agenda. I will briefly introduce Samza, Beam, and the Beam Samza Runner. Then I will talk about Beam Nextmark Benchmark Suite. It is the tool that we use to benchmark the performance. After that, Bingfeng will talk about how we identified performance bottlenecks and improved improve the performance for Beam Samza Runner step by step. At the end, we'll share with you our final benchmark results and some future works. There will also be a Q&A session. So let's get started. Samza is a distributed stream processing framework developed at LinkedIn in 2013. It is used for building stateful applications that can process data at scale in near real time. Then it became a top-level Apache project in 2014. And since then, Samza already has 14 major releases. Besides LinkedIn, Samza also used by many other companies, such as Intuit, Slack, TripAdvisor, and so on. So here are some facts about Samza at LinkedIn. We have more than 3,000 applications that process more than 2 trillion of messages per day from multiple sources like Kafka and Brooklyn. Our Samza applications are running on more than 3,000 machines in our Yarn cluster or in standalone mode as a library. In the following slides, I will talk about how Apache Beam and the benefits of supporting Beam API for Samza. So what is Apache Beam? Apache Beam is an open source unified model for defining both batch and streaming data parallel processing pipelines. By using one of the open source Beam SDKs, you can build a program that defines the pipeline. The pipeline is then executed by one of the Beam's supported distributed processing backends, like Blink, Spark, Google Dataflow, Samza, and so on. So Beam has some nice features. For example, it's a unified API that can be used for both batch and streaming use cases. It's portable, which means you can execute the same pipeline with different runners. It's also extendable by writing new SDKs, connectors, and transformation functions. Then, in 2018, we developed the Samza runner for Beam. What do we get from the integration with Beam? The Samza already has some nice features, like being scalable, supporting durable local states, backed by RocksDB, being fault tolerant, and so on. With the Samza Beam integration, we can leverage Beam's API to support more advanced use cases, like event time processing, sliding window, session window, and more. We also support Samza Python applications by using Beam's portability framework. And we also get SQL support from Beam as well. So now we have Samza runner for Beam. We would like to learn more about the performance. Performance is important for Samza as a data processing framework. Better performance allows Samza to scale in a more efficient way and hence reduce operational cost. And we also wanted to know how Samza runner performs compared to other Beam runners. Fortunately, in Beam, we have the Nextmark benchmark suite. In the following slides, I will talk about the Nextmark, which is the tool we used for benchmarking. So what is Nextmark? It was originally a paper aiming to design a set of queries that can be used to benchmark performance of stream processing frameworks. Then Apache Beam implemented it as the benchmark suite, and it's already widely used in the Beam community now. It contains a set of 15 queries in total, and then they can be used to benchmark both performance and the correctness of beam runners. The queries can be executed by different runners like the direct runner, Blink, Samza, Spark, and so on. As for the direct runner, it is the default local Java runner for verifying the correctness of a pipeline. Let's continue to learn more about Nextmark. So here's the data model of Nextmark. Basically, it simulates an online auction system. In this system, we have three classes: person, auction, and bid. A person can open an auction, and for each auction, there's an item associated with it. A person can also make a bid on an auction. Yeah, that's it. So this is a very simple system. And there are in total 50 Nextmark queries that cover almost all basic beam operators. There are some questions you may have about this auction system. So we can take a look at some example queries. For example, the input messages of bid are in US dollars. What if I want to have the prices in euro? We can use a map function to convert the prices from US dollar to euro. And that's what query 1 is about. And let's take query 7 as another example. I want to know what is the highest bid for a certain item in the last 2 hours. This can be achieved by using a fixed window of 2 hours, together with an aggregation function that keeps the highest price. So these 15 queries cover from simple operators like map, filter, to more advanced operators like different windowing strategies. This is an example output of running the Nextmark suite. The first column is the query number. For example, the second row is the results for query 0. The second and third columns are the throughput of the query, which is useful for comparing the performance. And the last column is the number of output events. It is used for validating the correctness of the query. Then we ran the Nextmark suite with Direct, Blink, and Samza runners. All of them use a single container with a single task. For Blink and Samza runners, we set the state store as RocksDB, and we also set the bundle size for all runners to be 1, which means each message was processed individually. So let's take a look at this graph. The x-axis represents the 15 queries. For example, query 0 is query Q0 is query 0, and the y-axis represents the throughput of a query. The higher is the better. Direct runner is in green, Blink runner is in red, and the Samza runner is in blue. As we can see here, Samza runner didn't perform well in basically every query. On average, the throughput of Samza runner is only about 20% of the direct runners and 10% of the Blink runners. And next, Bingfeng will talk about how we identified performance bottlenecks and how we improve the performance step by step.
Okay. Thanks, Yixing. Next slide, please. Yeah, I am Bingfeng from performance team at LinkedIn. So today I will take the performance optimization part. In the following time, I will share more details about how we successfully improved Beam Samza throughput by CPU profiling. As Yixing said before, we have a very large Samza cluster at LinkedIn. We have got a lot of machines, and when there's a lot of hardware involved, any little performance improvement you can make are going to help us to reduce considerable cost. So because of that, it's very worthy for us to try our best to optimize the performance of Beam Samza framework to save cost. Next slide, please. Yeah, although we have seen the performance gaps between Samza runner and the other Beam runners in the previous slide, according to our benchmarks by Nextmark, and we want to improve Samza runner. Identifying the important areas for performance optimization can be difficult for complex framework like Beam Samza. One large factor of this difficulty is how to identify bottlenecks by which we could achieve major performance improvements. And performance optimizations is an endless work in the engineering world, and we should know where our efforts can be best spent. So we are facing 3 questions before trying to do real work. So what are the performance bottlenecks of Beam Samza? Which part of the code or design can be improved? And which optimizations are the most worthwhile for us? Next slide, please. Our approach in this project is using profiling data to guide optimizations. We relied on data-driven investigations to determine the direction of performance improvements. There are multiple aspects of profiling methodology which are worth discussing here. To achieve the performance improvement goal, you should know how to profile the system, how to use data to prioritize the right things. So first, it is important to make the profiling right. We need to choose the right profiler and the right performance metrics. As Yixing said before, our goal in this project is improving the throughput by optimizing Samza runner framework. We are not trying to optimize performance areas such as runtime GC, memory, and CPU usage, etc. So we decided to use async profiler CPU mode to profile CPU cycles of running Samza job. It is to diagnose expensive computational hotspots. Then by analyzing the profiling results of expensive hotspots, we could target corresponding inefficient code or frameworks. Then we could optimize them so as to improve the processing speed of Beam Samza. Async Profiler is a good fit here since it is an open source and easy to use and low overhead sampling profiler to Java applications. It is also supported and automated at LinkedIn called on-demand profiling. We call it ODP. Secondly, being able to interpret the results and view them in meaningful ways is vital to properly identify the biggest potential performance wins and drive our performance optimization. For profiling results visualization, we use the frame graph. If you are not familiar with it, it's okay. I added an example of frame graph in the right side. You only need to know the y-axis shows the depth of our call stack. Each frame is a function call, and the parent functions are lower in this figure. An x-axis represents an aggregation of time it took that function to execute as a percentage of the total time of its parent function. The wider the bar on the x-axis, the longer the function has spent on the CPU. So you can see, in general, finding functions that are both high on the y-axis and wide on the x-axis is a great way to narrow down performance issues. So I will share more examples of how to use frame graph, the profiling results, to target performance issues of specific code blocks of Samza in the following slides. Next slide, please. So with benchmark tool and profiling tool ready, Nextmark and async profiler, this is our optimization steps. Step 1, we will choose the slowest next mark query and launch a standalone Samza job in our consistent testbed. Step 2, profile CPU time of running Samza job and identify expensive computational hotspots. Step 3, we will analyze the profiling results and optimize corresponding code or system design. Step 4, we will test the throughput improvements by next mark. Then we go back to step 1 and repeat above steps. We have done several rounds of optimization in this project. Overall, as the right table shows, we have successfully improved the throughput of Samza runner by 11 times, which is pretty good for us. In the next, I will share some examples and steps of how we gather the profiling data and use it to uncover performance issues, and the process involved to come to the conclusion we did. Next slide, please. So the first example I want to share is finding out duplicate code and redundant processing who have made the system lengthy and bulky. By checking the flame graph profiling result, we can easily identify redundant processing since they would have the same cost stacks and CPU cycles usage. For example, we have noticed that the matrix update method was always called 4 times in each element processing, as shown in the below screenshot of flame graph. You may say a few blocks of duplicate code of redundant processing might just use a few milliseconds to run. However, each millisecond of delay will contribute to a greater delay if it is executed thousands and millions of times every minute. Matrix update is a good example here. It has brought us a significant performance cost because Samza runner will extract and report a matrix during pipeline execution for each element processing in our test setup. So with this profiling result, by cleaning up redundancies, we have seen overall throughput improvement by almost 4 times. We can see saving cost by eliminating redundant processing is easy and simple, but very effective. Next slide, please. The second example is how to identify inefficient implementations by searching keywords in profiling results. So actually, some generic fundamental overhead, such as string concatenation, logging, and stack tracing might impact the system performance a lot if they are not well designed. So lucky for us, a flame graph supports searching by keywords to identify the footprint of these common costs. For instance, by searching the regular expression toString, we have noticed that the matrix key toString has a very high overhead in each matrix update. In this flame graph results shown in the left bottom, the matrix key toString has taken almost half of the CPU time in each process element function. And as we have discussed in the previous slide, matrix update plays a big role in the performance cost, so we definitely need to optimize it. By shortening the length of matrix key and also optimize the string concatenation, we have seen the throughput performance was improved by almost 2 times on average. Next slide. The third example I want to share today is how to learn the state-of-the-art designs from the other beam runners such as Flink by profiling results. During our optimization, we also have profiled other runners and compared them with Samza runner. By this comparison, we identified and also improved some inefficient designs of ourselves. As Yixing explained before, a beam runner is responsible for translating beam pipelines so that they can run on an execution engine such as Samza or Flink. CPU profiling results will provide a much more indicative view of the translation overhead of different runners. Hence, we can compare and understand the relative strengths and weakness of each runner. For instance, by comparing to Flink runner, we have noticed the inefficient design of Samza matrix container update strategy in each Purdue step. Its cost is much more than, the cost of CPU time in Samza runner compared to Flink is much more. So after improving this part with a new optimal design, we have seen performance improvement by around 1.3 times on average, which is also not bad. Next slide. Last but not least, benchmarking inefficiencies by statistical analysis of profiling results. As I mentioned before, being able to interpret the profiling result, is vital to identify the biggest potential performance wins for us. We also have analyzed the profiling results to identify the distribution of performance costs in Samza runner. For example, by calculating the serialization and deserialization cost in nextmark stateful queries, we have noticed that almost 38% of CPU time was spent on serial-deserial processing in each element process. To reduce the serial-deserial cost, we come up with a bet in-memory cache design to have a trade-off between speed and memory usage. Next, I will hand it over to Yixing again for the detailed design of the new cache framework. Yixing.
Hey, Yixing, I think you are on mute.
Yeah, thanks Bingfeng for the analysis. Let me continue with the optimization on the state cache. For each Samza task, there is a local state backed by RocksDB. So we also have the state cache, which is an in-memory caching layer in front of RocksDB. It helps us to avoid duplicate reads and writes against RocksDB. But the state values in the cache were already encoded, which means we couldn't avoid the deserialization cost of reading when cache hits. To optimize it, we updated the logic to hold the state values as deserialized Java objects in the cache. So here are the charts illustrating the change. Before the optimization, during a write, a state value was encoded by the coder into a byte array. Then the byte array was cached in memory and finally flushed to RocksDB. During a read, no matter the value was in the cache or not, we still needed to use the coder to decode the byte array back to the state value. Remember Bingfeng's analysis on the flame graph? Deserialization cost was high, so we wanted to avoid that in the case of cache hits. Then we optimized the code. Now we hold both the state value and the coder in the cache. Whenever a flush happens, the state value will be encoded by the coder into a byte array and written to RocksDB. During a read, in the case of cache miss, the behavior is the same as before. In the case of a cache hit, we can directly read the state value from the cache without the deserialization cost. With this optimization, we ran the test again with a large cache size that can hold all cache values in the cache, all the state values in the cache. The average throughput for the stateful queries has been improved by about 19%, which is very great. So after all the optimizations we have done, we ran the benchmark thread again for the Samza runner. Here are the results. The results for direct runner and the Flink runner and Samza original are the same as the initial results I just shown. The blue bars are the results for the Samza runner with optimization. So as we can see, the throughput for Samza runner has been improved a lot for each query. Overall, the average throughput of the Samza runner has been increased by 11 times. And now, Samza runner is on par or a little bit better than Flink runner. We also published the results in an engineering blog with more details. As for the future work, we can enable Samza runner to the dashboard for next mark results. Then we will be able to see the next mark results for Samza runner after each commit. And besides that, there are potential improvements we can continue to work on for bundling and multi-threading scenarios. That's all we have for today's talk. Thank you for joining us.
Awesome. Thank you, Yixing and Bingfeng, for sharing this with us. 11x throughput is extremely impressive. And Bingfeng, you also worked with our team, the Streams Infra team, to do some benchmarking for Brooklyn as well. So appreciate the great work that you've been doing. Looks like we don't have any Q&As. I have one question. So for increasing, it looks like you were trying to optimize for the throughput, trying to improve the throughput. Did that come at a cost of using more resources, like let's say memory or like cores? Any physical resources needed to be changed to get this throughput?
Yeah, I can take that question first. So yeah, basically our optimization contains two parts. The first one is kind of like reduce the redundancies of CPU consumption. Yeah, basically identifying the CPU, the computational hotspot, and try to optimize corresponding code of system design. So on this part, I believe we should also reduce the CPU, resource consumptions of some runner. But we didn't collect the metrics for this part because in our test bed, we just want to measure the throughput. On the other part is the cache. It's a new cache strategy Yixing just shared. For that part, of course, it's a trade-off. It's kind of like a trade-off between where if you want to cache the state data in memory to speed up your stateful query, or you want to use like RocksDB as a backend, and you can have a large state, but you will suffer the serialization and deserialization cost. So for that part, we have the configurations, and users can choose to, for this trade-off.
Okay.
Thank you.
Yeah, it makes sense. Yep. All right. Thanks again, Yixing and Bingfeng. Since we don't have any Q&A, we can jump directly into the next talk. Please welcome to the virtual stage, Efe.
Hi, everyone. Can you see my screen?
Sure can.
Perfect. Welcome to the second talk of today. My name is Adem Efe Gencer. I'm a software engineer at LinkedIn's Kafka team. Today, I will present how we made cluster maintenance operations faster and safer using this new concurrency adjuster of cruise control. So this talk will consist of 4 parts. First, we will take a look at how we manage Kafka clusters at LinkedIn and what it means to manage Kafka clusters. Next, we will delve into the details of concurrency cap to see its role in maintenance operations. Then we will discuss how concurrency adjuster fits in cruise control's architecture and how it works. And finally, I will share some results from our production environment. So now let's first go over how we manage Kafka clusters at LinkedIn. So for cluster management, we are using Cruise Control, and Cruise Control supports admin operations for cluster maintenance. It enables anomaly detection with self-healing. It provides real-time monitoring for Kafka clusters. With admin operations, we get the support to expand or shrink our clusters by adding or removing brokers. We can demote our brokers to transfer the leadership, all the leadership of replicas away from the demoted brokers. We can provide dynamic load balancing. We can identify and fix offline replicas, which might be the ones that reside on dead disks or dead brokers in our system in Kafka cluster. We can trigger PLEs. PLE stands for Preferred Leader Election. And when we trigger a PLE, it transfers the leadership within partitions to their most preferred replica for leadership election. So self-healing indicates an automated action to fix an identified anomaly. An anomaly could be due to a goal violation, a broker failure, a disk failure, slow brokers, misconfigured topics, or even due to a planned maintenance event, which is one of the newest additions to self-healing and anomaly detection. And the self-healing action depends on the type of the detected anomaly. For example, if we detect a goal violation, they are fixed by rebalancing the cluster. If a broker failure is detected, then the mitigation action is to make sure that all the replicas are moved away from the failed brokers. Disk failures are fixed by fixing offline replicas. So real-time monitoring enables our cluster operators, our SREs, to examine the distribution of replicas, leadership, and load in the cluster. And it also allows them to identify the partitions that are unhealthy. They're unhealthy because they may contain replicas that are falling behind, or they might be even completely offline. Hence, the clients, the producers, and consumers might be unable to produce to or consume from these partitions. Hence, they might be affected. Also, real-time monitoring allows us to inspect the health of brokers, disks, and user tasks in our system. So at this point, we know what Cruise Control provides. Now we are ready to examine the building blocks for managing Kafka clusters. So there are three key items, three key operations for doing so. And the first one is inter-broker replica reassignment. Another one is intra-broker replica reassignment, so within the broker. And the other one is, the third one is leadership movement. In this talk, we are going to focus on the first one, the first key item, which is inter-broker replica reassignment across the brokers. This figure shows a replica reassignment and inter-broker replica reassignment from broker 1 to broker 0. These small boxes indicate replicas. Their color indicates the topics that they belong to, and the numbers on them indicate the partition ID of them. So this replica move is a very powerful operation. It has a broad impact on the cluster. So what that means is that Cruise Control can satisfy almost all of, but not all of them, the majority of the admin operations, and again, the majority of self-healing actions using just a number of replica moves. With Kafka 2.4, KIP 455 introduced an admin API for performing replica reassignments. And Cruise Control has multiple versions in our open source repository. The versions of Cruise Control that supports Kafka 2.4 and after adopts this API for replica reassignments. And not surprisingly, moving a replica from one broker to another requires some data transfer. So there's a cost associated with this operation, and the cost might be higher depending on the size of the replica. So if it has gigabytes of data, of course, this will involve more data transfer between brokers. But that's not the only cost associated with a replica move. There is also something called metadata pressure. So metadata pressure happens due to the metadata propagation between brokers during an ongoing replica reassignment. And as a result of this process, the clients in the system, our producers and consumers, may observe some increased latency and even loss of availability issues. I believe the previous stream processing meetup, which was held in July of this year, had a talk from Krit Petty, an engineer in Kafka team at LinkedIn, and he talked about the details of metadata pressure. So if you're interested in learning more about the impacts of metadata pressure and how it can happen, please check out his talk, which is available, the recording of which is available in our LinkedIn engineering channel at YouTube. And even more critically, we observed that the side effects, the adverse effects of this metadata pressure on clients tends to grow with the growing scale of Kafka clusters. And LinkedIn has a really large scale Kafka clusters, maybe the largest scale in the world. So in particular, we have clusters containing over 300 brokers. We have clusters containing more than 1.6 million replicas, each having gigabytes of data on them. And overall, within the LinkedIn, we serve over 12 trillion daily messages on over 7,000 brokers. So these are really large numbers. And given this large scale, and given that replica reassignment operation is a frequent and integral part of this frequent maintenance operations, we would like to ensure that these operations do not affect clients, they're safe, and at the same time, they're fast. We would like to perform these operations within some reasonable time. We don't want them to take days. So for this purpose, Cruise Control has something called a concurrency cap. And this concurrency cap limits the number of replicas that can move in or out of a broker at any given time. So this figure will show how this cap works in practice for a replica move that is moving out of broker 0 and a replica move that is inside broker 0. So this cap used to be adjusted using some human-driven process. It was not automated before. So for example, if the cap was set to be 1, then this means in our example, we can only have one of these tasks active at a given time. So either a replica moves out of broker 0 or replica moves to broker 0 at any given time. They can't happen concurrently. And the priority of which item, which task will go first is pluggable. So cluster users, cluster operators may say they would like to prioritize larger replica movements first, or they may also say they want to prioritize replicas from not under replicated partitions first. So it's all pluggable. And another point is cluster operators need to do some adjustment on this cap unless they're fine with using the default cap for the whole executions in the cluster. But turns out this manually finding the optimal concurrency cap is a non-trivial process. It requires some effort. So in particular, if we want to set a proper cap, that typically requires examining the a subset of the broker metrics in the cluster during ongoing executions, which is a non-trivial process. If we set a high concurrency cap, the outcome that we get would be having faster executions in the cluster. So if we start a replica move, that finishes faster with higher concurrency. Whereas this high concurrency may also lead to overwhelm in the cluster, which can cause increased latency and availability issues to our clients. Whereas a low concurrency cap is safer. So it's empirically, the impact that we have seen on the clients is at minimum. But if you pick a low cap, the result here is excessively long maintenance operation times. So for the clusters that I just mentioned a couple of slides ago, with that scale, if you pick a low cap, we can observe maintenance operations that do not complete for multiple days. And so these investigation shows that the optimal concurrency is a hard to find value, and doing this manually requires multiple attempts to get it right. But even then, after finding the good cap, someone needs to readjust this cap because there's fluctuation in client traffic in the cluster, and these fluctuations make it necessary to adjust the cap. For example, these figures show incoming and outgoing network traffic on a typical Kafka cluster in our LinkedIn production environment. X-axis here shows the time in 6-hour increments. Y-axis shows the traffic in bytes. And note that the Kafka cluster does not and is not really expected to receive and serve a constant traffic. So the traffic continuously fluctuates. In particular, within any given day, we see fluctuations, and across the days of the week, there are also fluctuations. So the results in this particular case indicates that the magnitude of these fluctuations, which are measured in terms of average peak-to-dip ratio, within any given day were between 2.6 to 3.5 times. And across the days of the week were between 1.5 to 2.6 times. So these are large fluctuations. And given these large fluctuations, of course, setting up a proper cap manually requires a significant investment in terms of the effort to find out a nice value. And not surprisingly, and maybe naturally, our SREs didn't really have to set up a proper cap for each individual cluster that we have. So at LinkedIn, we used to use a safe cap, which has a low default value of 1. And this resulted in executions that were taking a very long time. So given these challenges, our goal here is to achieve a fast and safe execution of maintenance operations without human intervention. And to achieve this goal, we introduce concurrency adjuster as a new component of cruise control's executor. On the next couple of slides, we are going to discuss what concurrency adjuster is, how it fits in cruise control's architecture, and how it works. The high-level challenge that concurrency adjuster addresses is the automation of the dynamic adjustment of replica reassignment of concurrency. And to do so, it uses a feedback loop that adaptively increases, decreases, or maintains the current pace of ongoing replica reassignments. And this feedback loop uses a selected set of broker metrics along with some configurable thresholds, which we will discuss in a couple of slides. But let's first take a look at the workflow of the concurrency adjuster. So this figure shows the concurrency adjuster along with the relevant components that it interacts with. These orange rectangles show the pluggable components, and these pink rectangles shows the internal topic that cruise control and its metrics reporter use. So since these orange rectangles are pluggable, of course, users can use their own implementations or one of the other implementations provided in our open source repository. So for example, rather than using a metrics reporter, users may prefer to use Prometheus server to report the metrics. But regardless of where the source of metrics are, metrics sampler retrieves these reported metrics. And in particular for this presentation, we are interested in the metrics that are being collected during ongoing execution. But for completeness, let's take a look at all the metrics that are collected by metric sampler and what we do with those metrics, what cruise control does with those metrics. So cruise control uses them for modeling the broker and partition loads. This was an existing feature and still exists. It also uses them for slow broker detection, which is a process that is part of proactive mitigation. And with the concurrency adjuster now, these metrics are also being used for adjusting the speed of ongoing replica reassignments. So to do so, as a first step, concurrency adjuster needs to retrieve these metrics. And it does this by periodically fetching these metrics from the metric sampler. So there are a subset of broker metrics that are being evaluated by concurrency adjuster. And here are these metrics. There are 5 of them. Concurrency adjuster considers the 99.9th percentile of log flush time, follower fetch local time, consumer fetch local time, produce local time, and request queue size. So these are commonly used broker metrics that most of you in the audience should be familiar with. But there might be a question on why did we pick these metrics, why not others? So the key reason behind this choice is because we observe a strong correlation between these metrics and the observed latency and availability loss on the clients. So higher these metrics, worse the latency and worse the availability. And that's why we picked those metrics. And how do we use these metrics by concurrency adjuster is another question. So for that, we have configurable limits for each metric in cruise control. And if these configured limits are exceeded at any given time during an ongoing execution, concurrency adjuster's throttling algorithm kicks in to ensure that the ongoing replica reassignments are not too many. So we will see these details in a couple of slides. And another question is, are these metrics complete? Are they the only ones that we should consider and not look at anything else? So potentially not. Presumably there could be other metrics among the broker metrics, and in particular among the controller metrics, that might have also correlation between ongoing replica reassignments and its impact on the clients. So as a future work, we are also going to investigate if there is such correlation with the other metrics and expand this list further. So now that we know about these metrics, we can examine what we do with these metrics, what concurrency adjuster does with these metrics. So as part of the throttling algorithm, the concurrency adjuster uses them to automate the setting process of the concurrency cap. And in particular, when it looks at these metrics during an ongoing execution, if it sees that any of these metrics are under the all of these metrics, are under the upper limit set by the configurations, then it increases the cap by some value. And by default, the open source default value is 1. So every time it sees that all of the metrics are under their limits, the value of per broker concurrency cap is increased by 1. And similarly, if there are violations of these metrics, and if any one of them are being violated, then the cap is decreased by some multiplier. And again, in the open source, the default value for this multiplier is to divide the concurrency cap by half for each broker. So the astute members of the audience might have already realized that this is a version of AAMD, additive increase and multiplicative decrease. And the question might be, why did you pick AAMD? Why didn't you pick another throttling algorithm? And the key reasons behind this choice was basically it was simple and it was agile, so the changes were quick. And the overhead of this algorithm was also pretty low. And turns out this algorithm actually worked well for us. So these results are from actual production instances where we have a large Kafka cluster that's being managed by cruise control, and some replica reassignment is in progress. These figures show, the first one on the top shows the concurrency cap per broker that is dynamically changing, and it's being adjusted by the concurrency adjuster. And the figure on the bottom shows the total number of ongoing replica reassignments in the cluster. So x-axis here indicates the time in hours, and y-axis indicates on the top one the concurrency cap per broker, and the y-axis of the bottom figure shows the total number of ongoing replica reassignments. So the results indicate that there is a continuous change in concurrency cap throughout the execution, and you may notice that this shape of the change is sorted. So there's additive increase process, and there's multiplicative decrease process. And if you look at the top figure, we will see that as the concurrency cap increases on the top figure, we see that at the bottom figure, the total number of ongoing replica reassignments also increase. And similarly, as the cap decreases, we see a decrease in the ongoing replica reassignments. And over time, of course, we have a pool of pending interbroker replica reassignments. So they're not infinite, and over time they are depleted. And even if we increase the cap at a later point in time, we won't see as many ongoing replica reassignments. So that's the reason why we have this decrease on the bottom figure. And one other thing to mention is that there is this concurrency cap that is being maxed out at 4. And the reason for that is because this is a version of AAMD, and we have some other config that limits the maximum concurrency cap that our algorithm can move the concurrency cap to. So in our case, in this example, it was 4. So when it hit 4, it did not try to increase the concurrency cap further. Similar to this upper limit, there's also a lower limit that's also configurable. And in this example, the lower limit was configured to be 1. So one valid question at this point is, so giving everything to automation is fine, but as a human, I may need to intervene sometimes. And is that possible to do that in a fast, safe way? And the answer is yes. So first of all, at any given time, we can dynamically disable concurrency adjuster. We can stop it. And other than that, we can also stop an ongoing execution instantaneously. With Kafka 2.4, if we cancel some ongoing replica reassignment, we are not going to wait for the active replica reassignments to finish. So they will be canceled and rolled back immediately. So there are these safety nets around. But other than that, we can also dynamically change the concurrency cap ourselves. We can overwrite it. And if we do overwrite it when concurrency adjuster is enabled, then what's going to happen is if we set a limit that is too high, and if concurrency adjuster's throttling algorithm notices that our limit is violated, then the concurrency adjuster will force this cap down, and so that it will provide safety. And similarly, if we set this concurrency limit to a too low value, let's say that I set it to 1, but the cluster was not busy and I have resources to handle multiple reassignments within each broker, so that concurrency adjuster on those cases can increase the cap. So this also ensures that I'm not being too conservative. Also, before we conclude, I would like to talk about the other executor knobs. So far we talked about the concurrency cap, which limits the number of replica movements into a broker or out of a broker. But there are also other caps that we have when we run an execution. So first of all, we have similar concurrency caps for leadership and intra-broker replica reassignments as well. So just to reiterate, the intra-broker replica reassignment corresponds to a replica movement within a broker from its one log there to another. So typically this is done for JBot deployments. So if I have a JBot deployment, I would have multiple log theres for each Kafka broker, and each log there would reside ideally on a separate disk, so that with intra-broker replica reassignments, I can move a replica from one disk to another within the same broker. We also have a cap for that. Another thing we have is the byte rate throttling. So with KIP 73, we have now ability to throttle an ongoing interbroker replica reassignments based on the number of bytes that can be moved at a given time. And cruise control already has support for byte rate throttling. Another thing is execution progress check interval. This is also relevant because the execution progress check interval determines at what frequency cruise control updates ongoing replica reassignments. So let's say that I started 100 replica movements at time t. At some future time t plus 5, let's say, if I check the cluster again, I will see that there are some brokers that have available slots. So I can submit new replica reassignments for these brokers. So this frequency impacts how frequently I can fill out these gaps. And one other thing to mention is we have been working on concurrency adjusters for leadership movements and intra-broker replica reassignments as well. And I'm happy to say that cruise control today already has support for leadership reassignments as well. So if you are not using a JBot deployment, so cruise control already has all sorts of concurrency adjusters for all possible operations, because intra-broker replica reassignment is specific to JBot deployments. But going forward, we also would like to add support for this concurrency adjuster for intra-broker replica reassignments. So in summary, we have seen that cruise control's concurrency adjuster accelerated the completion time for ongoing executions, which involve inter-broker replica reassignments, which is majority of the time we have inter-broker replica reassignments, and that's the key time-consuming operation during ongoing executions. And with the concurrency adjuster, we have seen that the side effects observed on clients are disappeared now, because now there's an automated way to throttle the the execution concurrency, the concurrency cap during an ongoing execution. So it's safer. And maybe more importantly now, we do not need any human intervention in this process. So nobody needs to watch some ongoing execution and adjust this limit manually, which is really impractical to do so. So finally, everything that I talked about today are in open source. So today you can just go to github.com/linkedin/cruise-control. You can check out our repository. You can set it up within 5 to 10 minutes to manage your own cluster. If you face any difficulties at any given time, we have a community. So we have a Gitter channel that is very active, and we have people looking at it and try to help our open source community. And if you're interested in using our user interface to manage your different cruise control instances, let's say, you can have a dashboard that puts all these different cluster maintenance in a single dashboard using our user interface. And with that, I will take questions. Thank you.
All right, thanks, Efe. Great talk as always. We do have a few questions for you. So the first one is, how long does the replica reassignment take? Can it fail in between? If yes, is it an atomic operation?
Yeah, good question. So the time, first part is how long it takes. So the time it takes depends on multiple factors. One of them is whether the replica that I'm moving is a large replica. So obviously moving 1 gigabyte of data is not the same as moving 100 kilobytes of data. So that's the first factor. The second factor is my network capacity. So if I have some very high network capacity, very powerful network capacity, of course, again, the data transfer will complete faster as opposed to having weak network links. And the second part of the question is, what happens if there's something wrong during an ongoing execution? Can replica reassignment fail, or is it an atomic operation? So let's think about multiple scenarios that can go wrong. For example, if the destination broker dies, then cruise control will identify that the destination broker is dead. It will cancel and roll back the ongoing execution. So and it will also stop the ongoing execution. So in the end, you will end up with a cluster where everything is in a state that is predictable. So there is no corruption, there is no stuck partitions, stuck ongoing partitions, which used to be an issue, by the way, in Kafka 2.3, where if you have a destination broker that is dead, cruise control, again, was doing the safe thing. It was canceling the execution, but then you might have to do some controller bounds and replica reassignment Z-node deletion in order to unstick a stuck replica reassignment, which is no longer the case in Kafka 2.4 and after.
Awesome. So the next question is, and I think this question is specifically referring to one of your earlier slides in the presentation. So if you can scroll back to the one where you list the 5 criteria that concurrency adjuster considers. Yeah, so this one, the question was, why do you consider the 99.9th percentile instead of the max?
Yes. So based on our experience, the max seems to be, could be a one-off. So in a cluster where we have the max value considered, we see that this value is off the charts. But if you consider the 99.9th percentile, we observe a reasonable value where we can target and ensure that the almost virtually all of the clients that are using our system are going to be safe. They're not going to be affected by an ongoing maintenance operation. So that's why we picked the 99.9th percentile.
Yep, makes sense. And the last question that we have is, what is the feedback loop time from the moment that the metrics changed to the cap changed in order of like seconds, minutes, etc.? And is this time configurable?
Yes. So let me first answer the second part. It is configurable. So users can choose any time for this interval. And I believe the default value in the open source should be something like 5 minutes. So one constraint about this metric, this configuration, is that it cannot be smaller than the rate at which cruise control samples the metrics. So if you look at this figure, we see that this metric sampler retrieves reported metrics, either from a topic that the metrics reporter reports to, or maybe from Prometheus, if you're using Prometheus. But it also has some frequency. It doesn't continuously retrieve these metrics. And the maximum, let's say the minimum interval that one can set for the concurrency adjuster refresh time cannot be smaller than the rate at which the metrics are being sampled by the metric sampler. So that's the only limitation.
Makes sense. So this is all the questions that we had. Great talk again, Efe. Thank you all for attending again today. Our last meetup of this strange year. And we're looking forward to seeing you all again in 2021 and eventually, hopefully, having some live meetups again. So thank you all and have a good evening. Thank you.
Thank you.